Welcome to module number 4, virtual memory. So in this chapter we have covered the how the virtual memory is going to be implemented. There are two techniques, demand paging and demand segmentation. In this concept we are covered how the virtual memory is implemented using demand paging. So when you are demanding the page, if that page is not present in the memory, then how we have to know that page is there in the memory or not? We are using valid and invalid bits. If the bit is valid, the page is in the memory. If the bit is invalid, the page is not in the memory. If that page bit is invalid and it is not in the memory, then it raises or causes the page fault. When there is a cause of page fault, it will abort the execution of the process and it will trap to the operating system the page fault. When there is a page fault, OS will locate the page that is needed by the system, needed by the program, and it will try to bring into the memory. At that time it is going to verify is there any free frames available or not. If there is a free frames, then simply it will bring that page into a memory and it will update the page table. If that page if there is a no free frame, then it is need of page replacement. There is a need of page replacement. So page replacement algorithm will identify the victim page and it will swap out and it will make a free frame, and it algorithm will bring the new page and it will update the page table and it will restart the instruction. And we have seen the different page replacement algorithms to identify the victim page and to bring the page into the memory. There are three different algorithms we have covered: first in, first out, optimal, and least recently used page replacement algorithm. So these all things we have covered in the previous lectures. Now we'll go to the next topic, that is allocation of frame. This is another type of algorithm that we are using for allocating the frames. How the pages are going to be replaced. At that time we have seen there are two different algorithms. One is allocation of frames and another one is page replacement algorithm. Now we have discussed the page replacement algorithms. Now we'll go for discussing the allocation of the frames, how you are going to allocate the frame. Now the question is here, how do we allocate the fixed amount of free memory among the various processes? So for example, if we have a 93 free frames and there are two processes, how many frames does each process get? These are the two questions we have to handle or we have to solve using the allocation of frames algorithms. Whenever there is a process arrives or need to load into the memory, each process needs the minimum number of frames here. For example, IBM 370 6 pages to handle the SS move instruction. To handle this, there is a need of 6 pages. Instruction is of 6 bytes, might span 2 pages, and 2 pages to handle form means source place, and 2 pages to handle to means from which place to which place you are moving. For that, taking the data from to there is a required. The total number of pages required by this move instruction of system software is 6 pages. So now how many maximum pages we can allocate? Maximum of course is a total frames in the system. Maximum frames allocated for the process is how many number of total frames available in the system, that many maximum frames we can allocate for the each process. Not beyond that we cannot allocate here. Now the question is how to allocate here. That question we have seen here, 93 free frames are there and two processes are there. How many frames does each process get? To solve or to answer this question, we are using the different allocation schemes. One is fixed allocation scheme and another one is priority allocation scheme, and some other variations of allocation schemes. Those also we are going to discuss one by one here. So first of all, we will see fixed allocation scheme. Fixed allocation, again there are two allocation methods we are using here: equal allocation and proportional allocation. These are the two different methods we are using for allocating the frames. When there are more than one process or multi degree of multi-programming to increase here. For example, equal allocation means if there are 100 frames and there are 5 processes. Now we are equally distributing these 100 frames to all the 5 processes. Give each process 20 frames here. Keep some as a free frame buffer full. So like this we are allocating the frames equally to all the processes. This way we are going to dividing. Simply what we are going to do is number of frames divided by number of processes. Number of frames divided by number of processes. This is a method we are using for allocating the frames using fixed allocation in that equal allocation. So next one method we are going to discuss here. So what is going to happen here if you are distributing the frames equal to all the 5 processes. The process P1, P2, P3 are of 10, 5 and 15 frames are required till we are allocating the 20 and remaining all are going to become a wastage here. To overcome this problem, there is another method we are using in the fixed allocation called as proportional allocation. It will allocate according to the size of the process. What is the size of the process? Based on that, it is going to allocate the number of frames to the each process. So dynamic as degree of multiprogramming, process size change here. So as the degree of the multiprogramming is going to increase, the size of the processes or a process size is going to be changes here because it is a dynamic degree of multiprogramming. So consider one example here how actually you are going to distribute or allocate the frames using the proportional allocation. There is a one formula we are using here. AI is equal to allocation for process Pi is equal to Si divided by capital S into M. So what is Si here? Size of process Pi, and what is S means summation of all the processes, size of the all the processes. M means total number of frames. This is a formula we are using to calculate or allocate the proportional. One example you take here, the total number of frames available 64 here, and there are two processes S1 and S2. S1 size of the S1 is 10 frames and size of the S2 is 127. So now how you are going to allocate the number of frames here. For allocation for the process P1, A1 is equal to 10, size of the process is 10 and the total size of the process is 137. That is 10 plus 127 is 137 into 62. It's equal to, so at max we can allocate 4 frames are required to load the process P1 with size 10 here. So like that you are allocating number of frames to the process P2 by using A2 is equal to 127 divided by 137 into 62, and so equivalents 57 frames are going to be allocated for the process P2. So in this way, instead of allocating equally to the both processes, we are using your proportional allocation to allocate frames according to the size of the processes. These are the two methods we are using allocation of the frames using fixed allocation method. So we'll go to the next another method that is used to allocate the process called allocation of the frames using priority allocation. So use the proportional allocation scheme using priorities rather than the sizes here. So instead of size, we will go with the priority of the processes. If the process Pi generates a page fault, so now we are going to select for the replacement one of its frames. So which frame you are going to select for the replacement? Select for the replacement a frame from a process with a lower priority number. So means what, we are replacing the pages of the lower priority processes, that we are going to call it as a allocation of the frames using the priority. This is another method we are using for allocation of the frame, and some more methods we are using here: global versus local allocation. Global replacement means what here? A process selects a replacement frame from the set of all frames here. One process can take the frame from another process also possible here, but if there is a problem, process execution time can vary greatly, because if there is a one process executing and if there is a page fault occurs, now we are replacing the frames of another process that is being executed. So now there is a but greater throughput, so more common here. It provides a greater throughput, but it takes a more time for the execution. So to overcome this problem, we are using a local replacement. Each process selects from only its own set of allocated frames. So now we are going to replace only the frames, or we are making the free frames for the process when there is a page fault by replacing the pages within their locality or within their allocated address space. So it is more consistent per process performance, but the possibly underutilized memory. There is underutilization of the memory because we are distributing the memory equally, or we are using some methods called as a fixed allocation. In that we have studied equal and proportional allocation. If you are using the equal allocation, then equally the frames are distributed to many processes. There are some pre-processor available, they cannot be utilized. That is a problem we are going to face with the local replacement, that is called as underutilized memory. This is a problem we are going to face with the local allocation. So now when you are going for the page replacement, there is a problem. One problem we are going to face is called as a thrashing. So just consider what actually thrashing here. Before going to see the thrashing, we will take a one scenario. In fact, if any process that does not have enough frames, if any process that does not have enough frames, if the process does not have the number of frames it needs to support pages in a active use, it will quickly page fault. At this point, what you are doing or what the operating system will do, it must replace some pages from the memory to load the page that is required or active page that is required by the executing process or the program. So however, since all its pages are in active use, it must replace a page that will needed again right away, and consecutively it will quickly faults again and again and again, and replacing pages that it must bring back it immediately. And this paging activity is called as a thrashing here. So thrashing means a process is busy with swapping the pages in and out. It is CPU utilization is low, and the system or the process is busy with swapping pages in and out due to a page fault. And the process is thrashing if it is spending more time in paging than the executing. So process wasting most of the time in swapping out and swapping in the pages than the executing their actual instruction. This is called as thrashing here. And if process does not have enough pages and there is a page fault rate is very high, this leads to some drawbacks. That is, first one is low utilization of the CPU, because most of the time process is going to spend for swap out and swap in of the pages, and operating system thinking that it's need to increase the degree of the multi-programming because there is a low CPU utilization or the CPU is ideal. At that time operating system will load the another program into the memory, that is another process is added to the system and it will start the execution. So like that, if you go on increasing the degree of multi-programming, it will go at a one threshold, and after that it will start falling down, and it will increase the it will stop utilization of the or CPU utilization is go on decreasing here. That is shown in the diagram here. So at the beginning here, degree of the multi-programming, may some processes are there. When there is a page fault, they are busy with what? Page swap in and swap out. So at that time CPU utilization is good. So when there is a degree of multi-programming will go on increasing, and there is a not all the processes are in the memory. The part of the processes are there in the memory to begin the execution, and remaining part are in the backing store because there is a lack of storage space or lack of free space in the physical memory. As you know, that size of the memory is less. So as you go on increasing the degree of multi-programming, and there is a low CPU utilization, afterwards what it is going to happen here, due to the degree of multi-programming, most of the processes or all the processes are going to spend their time for replacement. They will spend the time for replacement, moving the page out from the memory and bringing the page into a memory. So it will decrease the CPU utilization. So when the thrashing occurs here, you go increase the degree of multi-programming, there is a decrease of CPU utilization, that is called as thrashing. So now question is here, how to control the thrashing, that we will see here. Control of thrashing. So demand paging and thrashing. To prevent the thrashing, what we have to do here, we must provide a process with as many frames as it needs. Instead of loading the partial part of the process into the memory, we load entire process in the memory. But how do we know how many frames it needs here? There are several techniques we are going to use for the control for the thrashing. One is working set strategy. Starts by looking at how many frames a process is actually using. This approach defines the locality model of the process execution. So locality model states that the process executes, it moves from locality means the process that is means when there is a page fault occurs, what we are going to do here, we are going to move the pages, we are swapping out some pages, or entire program or process may also swapped out and new process will be swapped down. That time the process that is swapped down, later you are going to swap in, that time it is going to move the different locality. So locality is a set of pages that are actively used together by the process, and a program is generally composed of several different localities which may overlap here. So why does thrashing occurs? The thrashing occurs because the size of the locality is greater than the total memory size. This limit affects by using the local or priority page replacement algorithm. This is a problem we are going to face. So to overcome this problem, we are going to use a working set model. This is a working set model we are using to overcome the thrashing problem. So what it is actually, working set model is, it is based on the assumption of locality. This model uses the parameter delta to define the working model or working set window. To define the working set window, we are using a delta here, and working set window is a fixed number of page references. For example, 10,000 instructions. So here the idea is to examine the most recent delta page reference here. So set of pages in the most recent delta page reference is working set, and that is shown in the figure here. This is a page reference table, and there are two windows, WT1 and T2, WST1 and WST2. And the first window there is a page reference is 1, 2, 5, 6, 7, and in the second window 3 and 4 here. So here what it is going to happen here, WSSI means working set of a process PI is equal to total number of pages referenced in the most recent delta. Delta is going to varies in time. If the delta is too small, will not encompass entire locality, means entire program is not going to be locality. If delta is too large, will encompass several localities, and if the delta is equal to infinity, will encompasses entire program here. If there are multiple localities, entire program is going to be encompasses. And here is a one formula we are using here, D is equal to WSSI, the total demand frames. D is called as what here, total demand frames. Approximation is locality here. Now when the thrashing is going to occur, if D is greater than M, then there is a thrashing. If the D is greater than M, then there occurs the thrashing here. If consider this example, in the WS window T1, if delta is equal to 10, in the given sequence of memory references shown above in the figure, if delta is equal to 10 memory reference, then the working set of time T1 is 1, 2, 5, 6, 7. Then by time T2, the working set model is changed to 3, 4 here. So then the second working set time, it is going to change to a 3, 4 years. Like this, the working set model is going to change based on the time here. So approximation with the interval timer plus a reference bit we are going to consider here. For example, keeping the track of working set here. How to keep the track of working set? If delta is equal to 10,000 instructions, time interrupts after every 5,000 times units. Keeping in memory 2 bits for each page, whenever a timer interrupts, copy and sets the value of all the reference bit is equal to 0. If one of the bit in the memory is equal to 1, page is in working set here. So you have to remember it. If any one of the bit is set to 1, means that page is in the working set. So implement 10 bits and interrupt every 1000 time units, so it will give the better performance to overcome the thrashing here. This is about the thrashing. There is another more direct approach than the WSS working set window to overcome the thrashing, that is establish acceptable page fault frequency, PFF, rate and use the local replacement policy. If you use the local replacement policy, or it is also called as a priority replacement policy, means they are going to replace the pages within the process region. If the actual rate is too low, process loses the frame. If actual rate is too high, process gains the frame here. That is shown in the figure below. Page fault rate and the number of frames. Increases the number of frames, upper bound. Decreases the number of frames, it is going to lower the page fault rate here. This is how actually we are going to control the thrashing here. Thrashing means what actually we have seen here. If the total number of frames required by the process is greater than the size of the memory or the locality or a working set window, then there is a page thrashing going to occur. So now if there is a thrashing, the utilization of the CPU is going to decrease here. So it should not happen, because if you decrease the utilization of the CPU, or CPU is idle, and most of the processors are going to spend their time for swapping the page in and out instead of executing their task, then the performance and the response time of the process is going to start decreasing. To increase that throughput and response time, we have to control the thrashing. And this is the end of the chapter 9, that is virtual memory management. Thank you.